So let's talk about precipitation reactions. We introduced them in the first section. Talked about sodium carbonate in laundry detergent softens the water by getting rid of the magnesium and calcium ions. Those reactions are example of precipitation reactions. So a reaction that forms a solid when you mix two aqueous solutions. So you've got two dissolved solutions, two liquids, you mix them together, you get a solid. That's a precipitation reaction. Here's an example of one. Potassium iodide is soluble. You can look at the rules and figure that out. Lead 2 nitrate is soluble. When we mix these together, they're both colorless, clear liquids, we get this bright yellow substance being formed. It's a precipitate. So it kind of looks like a cloud or something, right? It doesn't necessarily look solid because it's floating and swirling around. We know it's a solid because it's opaque. You can't see through it. It's not just a change in the color, but it's not clear anymore. It's opaque like milk. You can't see through it. The reason you can't see through it is because it's containing larger particles, much larger than individual molecules and atoms. And so it blocks light. The products are lead iodide and potassium nitrate. Well, how do we figure out what the products are and which one is going to be the solid and which one's going to be aqueous? Precipitation reactions don't always happen. You can't just mix any old aqueous solutions and get a precipitate. If you mix potassium iodide and sodium chloride, you've got a clear liquid and a clear liquid, you mix them together, there is no chemical reaction. There's a physical change because now they're mixed together, but we didn't see a color change, there was no heat or light, there wasn't a solid forming, there wasn't a gas forming. It just mixed. It's not a chemical reaction. So in a precipitation reaction, we're going to look at the products that could possibly form, and we're going to use our solubility rules to identify which ones would be insoluble. Only the insoluble combinations can make a precipitate. So what happens in these reactions, we have two solutions containing soluble compounds that when we mix them, one of the new combinations is insoluble. So let's look at what happens when potassium iodide and lead nitrate are mixed. Before mixing, the potassium iodide has iodide ions and potassium ions, and they're swimming around. And over here, we've got lead ions and nitrate ions, and they're swimming around, they're soluble. Okay, I've told you before, I think of metals as masculine and nonmetals as female or feminine. So I think of this as potassium's the guy and iodide is the girl. And they're hanging out together, but they're just like hanging out together. They're friends. And over here is lead, he's the guy, and nitrate's the girl, and they're hanging out. It's not like they hate each other, but they're not like a couple either. Okay? So here we've got these two friends and those two friends, and they're going to go to a party. And when they go to the party, now we've got these two solutions mixed in the beaker, and as they mix together, potassium, who came in with iodide, they're friends but nothing special, right? Potassium sees nitrate, and he's like, oh, hi, nitrate. Yeah, you're nice, but nothing special. Lead came in with nitrate, which, he likes her okay, but not strongly attracted to her. And then lead sees iodide. And he likes her. She is fine, and there is chemistry. They're like, whoa. And iodide thinks the same thing. It's like, oh, my goodness. And they're like, psst, they get together, right? You maybe have seen that happen at a party. They're not going to mingle anymore. They're going to find a couch in the back porch, and they're going to be making out. They are out of the party, right? They are together. They're stuck on each other. That's a precipitate. Why did that happen with lead and iodide when it didn't happen with potassium and nitrate? The chemistry is different, right? unlike with human relationships, we have a set of guidelines that helps us to predict who's going to like each other that much. Doesn't work with people. You can maybe guess, but oftentimes we're wrong, right? That's what happens with blind dates. So we look at the possible combinations of the ions, and we see if one of those combinations would be an insoluble compound. That's the precipitate. So the lead iodide precipitates, there they are, having a great time together. And these guys, what are they doing? Well, they're just at the party. They're hanging out. Did they get changed? No, they didn't get changed. Are these guys changed? Yeah, they're changed. Any questions? Nobody yet has asked me, well, where could I find iodide? So we're going to use this method for predicting the products for precipitation reactions. And we're going to look at the ions that come in, the guys and the girls, guy and girl, and then we're going to swap partner and see if there's chemistry between either of those couples. So the guidelines here are first write the formulas for the two compounds that are being mixed as reactants in the chemical equation. Then below the equation, write the formulas for the ions. Be sure to include the charges. This is going to make your life easier in the rest of the problem. Exchange the anions, swap the partners, rewrite the formulas, and then see if either combination makes an insoluble compound. If both pairs are soluble, you just write no reaction. You're done. That happens, right? That happens probably more often than not. A bunch of people come to a party, they mix, they have a great time, but nobody gets involved in a serious relationship because of it. Question?
Okay, how will you know which anions switch?
There's only two. We're just talking about two couples, a guy and a girl, guy and a girl. We're going to swap girls and see what happens. So if one of the pairs is insoluble, then you got to finish it up. So you write the formulas for the compounds, use AQ to indicate the one that's not soluble, the one that is soluble, and S to indicate an insoluble product. Okay, now here's an unfortunate coincidence of letters. Soluble starts with S, and solid starts with S. And so what does this S mean? S is a physical state. S means solid. AQ means dissolved in water. The soluble one is aqueous, it's dissolved in water. So try not to get those mixed up. Then you have to balance the equation. Again, don't change any of the subscripts. So let's see what happens here. So write an equation for the precipitation reaction that occurs, if any, when solutions of potassium hydroxide and nickel 2 bromide are mixed. So what are we going to do here? Well, we need the formula for potassium hydroxide. And to do that, we really should write each of the ions with their charges. So potassium and hydroxide. We look at the charges, we put them together. We get KOH. Here we are told that these are solutions, that these are soluble, but you could look it up if you want in the table. And then we've got nickel 2 bromide. So we have Ni 2 plus, and bromide is Br minus. So we look at those charges and we see we need 2 bromides for 1 nickel. That sounds like a special. I'll give you 2 bromides for a nickel. Let's see. You didn't like that? I thought that was pretty good. Okay? So you need to write these formulas anyway so that you can correctly write the formula for the compound. This is the work you need so that you can predict what's going to happen with the products. So here I have a guy potassium, girl hydroxide, guy nickel, girl bromide. We're going to swap partners and see how they like each other. So nickel is going to be with hydroxide, and potassium is going to be with bromide. These sorts of attractions in ionic compounds are based on opposite charges, opposite electrical charges. So we can't have the two guys being together because it's based on electrical charges, right? And so that's where sometimes analogies break down a little, but they're still useful. Okay, so I'm going to put potassium with bromide. So I'm just going to write them over here with their charges again, potassium and bromide, and then nickel, 2+, and hydroxide. Now I need the table so I can identify, is this potassium and bromide, is that soluble? Is nickel and hydroxide soluble? So we'll go back to the table. Oh, it's tedious. There we go. So we had potassium. Oh, potassium compounds, always soluble. So potassium is that guy that, you know, he's likable and all, but he just never gets in a relationship with anybody. These guys here, completely phobic to commitment. They're not going to commit to anything. They're just not interested. And these are the girls that don't get into relationships. So potassium and nitrate, they're going to hang out, but there's not going to be a relationship. So that would be an aqueous product. It's still going to be dissolved. The other one was nickel and hydroxide. And we look here, don't find either of those up there. Here's hydroxide. Nickel doesn't show up here at all. Hydroxide, mostly insoluble. Okay, she'll get it on with almost anybody, except these guys. And then these guys here with calcium, strontium, or barium, slightly soluble. Nickel is not on here. Nickel hydroxide is insoluble. So this one is going to be a solid. That means we've got to precipitate. We need to finish the chemical equation. So I'm going to put those two together and write the state symbol, aqueous. That was just +1, -1, one of each. Here I've got a +2 charge and a -1 charge. So I need 1 nickel with 2 hydroxides. And from looking at the rules, we know that that one's going to be a solid. Now we need to balance the chemical equation. Well, here I've got 1 potassium, and over there I got 1 potassium, so that's cool. Here I've got 1 hydroxide. You see, hydroxide stayed together. She just switched partners. So here's 1 hydroxide, and over here I have 2 hydroxides. So I need to put a 2 in front of potassium hydroxide. Oh, well, that messed up my potassiums. So now I've got 2 potassiums. Let's go fix that before we forget. I need to put a 2 over here. So 2 potassiums. Okay, let's go on. Nickel. There's 1 nickel and 1 nickel. 2 bromines and 2 bromines. There we go. Any questions? Let's do another one. I'm going to do these a little faster now. So precipitation reaction again. Here, ammonium chloride and iron 3 nitrate. So ammonium chloride. Ammonium is NH4 plus, and chloride is Cl minus. So I put those together. I get NH4Cl. And I'm told that it's a solution. This is aqueous. Iron 3 nitrate. Iron 3 is Fe, 3 plus. Nitrate is NO3 minus. Why? Because it is. So I'm going to get FeNO3, 3. I need 3 of these -1 charged ions to make up for the +3 on the iron. That's also aqueous. And now I'm going to swap partners. So ammonium with nitrate, iron with chloride. So let's see, iron 3 plus and chloride, ammonium.
Does it always go the 2 outers with the 2 inners?
It will always be the 2 outer with the 2 inner. Yes.
Does it matter the order you write them on the right side?
No, it doesn't. Excellent question. So I'm going to write iron 3 plus and chloride together in this order, but I could have these guys second, and I could have the ammonium and the nitrate first. Because it's just like math, adding. 2 plus 3 is 5, and 3 plus 2 is also 5, right? The order in which you add things doesn't matter. The order that I write the ions in does matter, though, because just like on a formal invitation, it's always the guy first and then the girl. It's the positive and then the negative. You have to have a positive and a negative, otherwise nothing's going to happen. So then I will find these in the table of solubility rules. So I'm going to use the one in my head. So I'm on the first line. I'm looking for iron 3 and for chloride. And I go down a couple into the top part, and I see chloride is mostly soluble, except lead 2, mercury, and silver. Oh, this isn't one of the exceptions. This is soluble. And then I look at these guys, and first up is ammonium. Ammonium compounds are always soluble. Both of these compounds are soluble. There's no solid that is formed. There's no reaction. It's mixing as well. It's a physical change called mixing, but there's no chemical reaction. And so I just write NR for no reaction. Done. Any questions? Let's do another one. I don't know why they had this on here. If no reaction occurs, write no reaction. That should be like on the first one. Anyway, write an equation for the precipitation reaction, if any, that occurs when solutions of potassium sulfate and strontium nitrate. Okay, so potassium is K plus, and sulfate, SO4, 2 minus, because it is. Then I've got strontium is 2 plus, group 2. And nitrate is NO3 minus, because. So I put those ions together in a way that their charges will add up to 0. So I need 2 potassiums with 1 sulfate. That's aqueous, because I'm told that these are solutions. Strontium and nitrate, I need 2 nitrates, so the charges add up to 0. Aqueous. Now I'm going to swap partners and see if anybody gets excited. K plus with NO3 minus, and strontium with sulfate. So potassium and nitrate. Potassium compounds are always soluble. Nitrate compounds are always soluble. Strontium shows up as an exception to some things. So you find sulfate. Sulfate is in the top half, where sulfate compounds are usually soluble. If you look at the exceptions, strontium is one of the exceptions. So this one's insoluble. So we do need to finish this one. So KNO3, that one's aqueous because it's soluble, and SrSO4 is a solid. It forms a solid because it does not dissolve. Then we have to balance it. I have 2 potassiums here. I only have 1 here, so I need to put a 2 in front of potassium nitrate. over here I have one sulfate ion, over here I have one sulfate ion. Here's one strontium ion, one strontium, two nitrates, lo and behold, two nitrates. Done. Any questions? Yes?
So you said that, when you look at the table here, you find that the sulfate oxide is the reason SO4, that's the reason why the exception for SR2?
Yeah, sulfate, here, let's actually go back to the table. I should stick one in here so I don't have to go this far. So if we look here, sulfate compounds are mostly soluble, except when sulfate pairs with strontium, the compound is insoluble. Okay? It looks a little different. It's maybe worded a little differently than what's on the green sheet.